Welcome back to Intro to Physical Anthropology. I'm David Leitner, I'm your instructor, and today we are going to be, sorry about that, a little noisy piece of paper blowing in the wind there. We are going to talk about primates. Primates, all of our cousins, a whole bunch of them. Actually, today we're going to focus just on what a primate is anatomically. How do we distinguish primates from other kind of mammals? And what that kind of says about the evolution of primates as well. What are some of the general tendencies we share with all primates, that all primates share with each other? So, without further ado, let's get started. So, there are 5 to 10 million species of animal estimated. That's a big sort of guess there. We don't know for sure at the moment, but the estimates range from 5 to 10 million. Of them, mammals make up about 4,000 species, and they fall into 3 different groups. You have the Metatheria, which are give birth, live birth, but without placentas. So that's your marsupials, for instance. You have the Prototheria, which may be sort of the most primitive form. It doesn't mean they are primitive, but they're probably the most like the first mammals, in that they still lay eggs, but once the young are born, they are suckled as well. In fact, that's where the name mammal comes from. It's the same root word as mammary, as in mammary glands, which produce milk, because that is the one trait all mammals share, is we suckle our young. There are only 2 living prototherians. They are the echidna and the platypus. And finally, you have eutherians, which are placental mammals. They give live birth from a placenta, and suckle their young. It's most of the mammals we think of. It's the kind of mammal we are. It's the kind of mammal all primates are. Now, mammals were not a terribly diverse group up until about 65 to 55 million years ago, maybe 50 million years ago. Up until that point, of course, the dominant animals on the planet were the dinosaurs. And for the most part, mammals kind of took a back seat. Most mammals by then were, although they started off as sort of, roughly the size of very large dogs, about 200 million years or so ago, by the end of the age of the dinosaurs, most mammals were sort of small, kind of rodent-y sort of looking things. After the dinosaurs disappear, that makes room for there are now a whole bunch of ecological niches that need to be filled, and mammals go into them. They fill them out like crazy. And you have this huge explosion in biological diversity among mammals, and you get all of the major orders of mammals, including the primates. Now, the most diverse today are Chiroptera, the bats. Are Rodentia, and right behind them are Chiroptera. And then you have Insectivora, Carnivora, and marsupials come last, just behind the primates at around 300 species. That's the non-human primates. Now, these numbers and counts are always a little rough because it depends on how the researchers are counting species, and whether they're combining certain species or dividing them up into subspecies and that sort of thing, and which databases they're using. So, but they're all roughly the same. As you can see, the primates themselves are quite diverse. In that 300 species, we have several divisions that have happened over the course of evolution, starting with a split between what we call strepsirrhines and haplorhines, which the strepsirrhines include the sort of the creatures that are probably most similar to the primitive primates at the time of that split, which are the lemurs and the lorises. Haplorines include everything else: tarsiers, New World monkeys, Old World monkeys, and the apes and humans. Okay, we belong in this category of ape. We share the most anatomical and genetic relatedness to them. That New World, Old World monkey split is something we'll talk about next time, and in greater detail, in particular, sort of what happened to the Hominoidea, the sort of group of apes and humans leading to us. Okay, but why are we bothering? If anthropology is the study of humans, why study primates at all? Well, first of all, as you can see from this cladogram, it's sort of phylogeny, actually. You have the time element here. Go back to last chapter's videos for that. We all share a common ancestor somewhere around 63 million years ago. So we all share traits as a result, in various degrees, depending on our genetic distance from one another. As you can see, Homo, that is humans, are very, very closely related to Pan, the chimpanzees, and then the other great apes, and then all of the apes together, and then to Old World monkeys, New World monkeys, and tarsiers, and then the rest of the strepsirrhines. So that's one good reason to study them. The next is that studying other primates, because of this evolutionary relatedness, gives us clues to how natural and sexual selection have shaped us since our divergence from our close cousins. It gives us clues in their anatomy, in their genetics, and most importantly, in terms of behavior. There are certain behavioral traits that are shared among all primates, or most primates, that are very, as we'll see in a future video, very important and defining traits of humans as well. Okay. So, yes, we share a relatively recent common ancestor. Gives us clues. Most importantly, though, the primates are fascinating. This is a famous meme. I don't know if you guys remember it or not. It was going around, about 5-6 years ago? I can't remember exactly. Looks like this monkey is smiling for the camera that it picked up. Well, it's probably more likely that it thinks it sees another ape and is baring its teeth as a sort of slight warning, saying, I don't know who you are, just stay where you are here, and happened to accidentally snap a shot of himself at the same time. So, but that in and of itself is almost more fascinating, I think, than if he really was taking a picture of himself, right? And smiling for the camera. Okay, so what is a primate? We all share certain characteristics, but it's important to understand that, although sometimes we use words like primitive characteristics and so forth, we don't actually mean that some living animals are less evolved than others. We've all been evolving for the same amount of time. We are all just as evolved as the others. It's just that we all evolve through different forms of natural selection, sexual selection, and the other forces of evolution. It has all shaped us into what we are. No traits are inherently better than other traits. So we need to sort of get that sort of evolutionary ladder idea out of our heads and start thinking more like that cladogram, where we're all kind of on the same level here. Just because a trait evolved very deeply in the past doesn't mean it's inferior. And just because we have evolved to lose certain traits doesn't mean those traits aren't valuable for other species. The most important thing to remember, though, is we need to make a distinction between living primates and our most recent common ancestors with those primates. Remember, the most recent common ancestor is between chimpanzees and humans, which existed around 6 million years ago, was not by default a chimpanzee. Okay? Instead, chimpanzees and humans have been evolving separately for 6 million years from something that was a little bit like both of us and a little bit not like either of us. So it was its own species. It was its own organism. So keep that in mind as well. You know, the most recent common ancestor isn't by default the less human of the options there. Okay. Okay, so what are some of these features? One of the big ones is we all share a generalized body plan. What do I mean by generalized? Well, in evolution, we talk about generalized versus specialized traits, okay? Specialized traits can only be used in specific ways. They are specialized for a particular task. Generalized traits maybe aren't as efficient at the tasks they do, but they can do a wider range of those tasks, and they can be adapted behaviorally to other things. Most primates lack a lot of specialized traits. That doesn't mean none of us have specialized traits. Bipedalism in Homo sapiens is an extremely specialized trait. We have very few options for locomotion other than bipedalism, in fact, because of it. So it's an incredibly specialized trait, as we'll find out in future chapters. But that doesn't mean the rest of our body plan isn't quite flexible in terms of how we use it. Indeed, the remnants of our own ape ancestors who at one point swung in the trees to get around. What's called brachiating, swinging from the trees, or doing suspensory climbing like this orangutan you see at the bottom here. We have adapted, even though we don't do that anymore, we are adapted to now use it to throw things. It's the same architecture in our shoulders, and that same freedom of movement allows us to, instead of propelling ourselves through the trees from branch to branch, to instead propel projectiles through the air at targets. So generalized body plan just simply means that most of our features are generalized rather than specialized. If you look at locomotion with most primates, although we may have a primary form of locomotion that we do more often most primates can in fact engage in several kinds of locomotion. It's somewhat adaptable. Whether you're talking about the difference between arboreal and terrestrial quadrupeds, their feet are slightly different, depending on which they're more specialized for. But there's nothing keeping an arboreal quadruped from walking on the ground. Nothing stopping them. Many apes, especially chimpanzees, will walk short distance as bipeds. They don't have the full bipedal architecture, but they are able to do it. We spend most of our time walking on the ground, but as anybody who grew up somewhere with trees knows, we can climb in trees just fine. With pretty good results if you're used to doing it. So that's generalized body plan. The next big trait are these things. Opposable thumbs. Only we're the only primate that doesn't have opposable large digits on our hind limbs. Our hind limbs have fused because of bipedalism. So our big toe, here's my thumb. I know that's not my big toe, so don't make comments, please. But if this were my big toe, instead of being able to do this with it, it is bound up by ligaments and through the way that the bones have developed and grown to become into line with the others, and that's an adaptation to bipedalism we'll talk about in the next chapter, in a couple of chapters. But the trait is still there. That big toe is still there. You can see the remnants of this trait of having opposable large digits on all of our hands and feet. The same is true of all primates. They have grasping fingers and toes. This is important because this allows for a precision grip. We have a much more precise grip because of shortened fingers and shortened palms that we developed after becoming bipedal. And our phalanges are straight instead of curved because we're not adapted to grasping onto things. And so we have even more precise grip than other primates, but all primates have better precise grip than, say, a cat. Although I've seen cats do amazing things. I haven't seen one yet that has mastered remote control. So, that's got to be the signifier of true animal genius, I think. So, now, along with those opposable thumbs come flattened nail beds. We don't have claws, with a couple of exceptions. I'm going to say that for everything, by the way. This is biology, not science. Science is not a science. We'll put it that way. Flattened nail beds allow for a wider grasping surface on the finger pads. This is better for precision grip and for getting more surface area for grasping onto things like branches and trunks when you're climbing. This is a common trait in all primates, with a couple of very key exceptions. There are a couple of strep screens that may have a claw that they use for spearing insects with. And it looks like actually they lost it and then gained that back later. So it appears to be a derived trait of those species, rather than having just held on to it from the past. So the trend holds. We all, at some point, lost the claws and got flattened nail beds. And the other exception are a few species that use them for grooming. So, forward-facing eyes. Now, you may have heard that forward-facing eyes are a sign of predators. It's sort of true. It's a sign, as we'll find out, of anything that needs to track things that move very quickly in front of it so that they can grasp them or catch them in some way. And the kinds of prey may not be what you think of when you think of predator. Okay. Forward-facing eyes give you stereoscopic vision at the cost of your peripheral vision and any vision behind your head. As you can see from the visual fields here, the rabbit has a very narrow field of binocular vision in front, very wide fields of monocular vision on the side, and a very narrow field of binocular vision in the back. It doesn't really need the binocular vision very much. It mostly needs to be able to detect movement. So if a predator is coming or moving in the bushes around it, it needs to be able to see that. So it's prioritized a wide field of view, almost 360 degrees around its head, whereas primates don't rely on that. That doesn't mean we haven't been or aren't predated upon, but what it means is our food oftentimes is trying to get away from us as well. And so we have a very wide field of binocular vision in front, narrow field of monocular vision to the side, and no vision whatsoever behind us. Now, these last several traits are ones that the explanation for which has been sort of debated for a long time. originally in the 1920s, one explanation that came up was the idea of the arboreal hypothesis. This has largely been abandoned at this point. Woods Jones and Elliott Smith, those are both last names, held that these are all traits for living in trees. Okay, you need binocular vision to be able to see branches and move around and jump from branch to branch and trunk to trunk and so forth. In the 1980s, people started pointing out there are a lot of holes in this. Like, lots of arboreal creatures don't have these traits. Squirrels do not have stereovision. They have vision. They have a narrow field of stereoscopic vision, but mostly their vision is on their side. They don't have nails. They have claws, as you can see up there. Although they can sort of grasp, they can't completely oppose their thumbs. So they can't sort of really get good grips the way that primates do. So another theory, the visual predation hypothesis, developed, which says early primates would have been insectivores living on the trunks or very near the ground of trees. So they needed to be able to quickly catch prey in front of them that was moving quickly so that they could survive. This was the niche they chose. Now, more of this sort of is suggested in our teeth. You know, just like our body plans are largely generalized, so are our teeth. Teeth are really great in evolution for two big reasons, because number one, they're already fossilized, they're already mineralized bone. And so oftentimes there are a lot of species, especially of small mammals, that we only know from their teeth. No other bones, you know, a tiny animal, most of the bones aren't going to fossilize or even survive, but the teeth do. And so we have lots of teeth telling us about a lot about an organism. Teeth are heavily selected for in natural selection because they are how you get your food. They're how you get energy into your body. And the more efficiently you can get energy into your body, the better your reproductive fitness. So the things you use to process food, your teeth, are going to be heavily selected for. So teeth actually change quite a bit in evolution. And they are abundantly available in the fossil record. Generally, non-human primates have small teeth that are neither, like on top here, the carnivore is very sharp teeth. In fact, actually, the carnivore, you see that rear premolar here, the last one, the biggest one, is called the carnassial. These teeth work like scissors, like shears, to scrape meat off of bone, okay? So we don't have teeth that are like that. But they're also not specialized for grinding things the way that herbivores are. Herbivores have these long, very striated, sort of ridged teeth that pretty much just do that. And you notice they have very few other kinds of teeth. They have a few incisors to help clip things and get things into their mouth, but otherwise it's all focused on grinding. Well, in primates, evolution has favored a generalized plan. We have 4 kinds of teeth that do very different things, none of which are perfect. Okay? But because it's a combination, we are able to eat a wide variety of foods. So we refer to the makeup of the mouth, of the teeth in the mouth, as the dental arcade. And the dental arcade is basically the arch formed by the jaw and the composition of teeth in one half of that jaw. And it's expressed as a set of numbers representing incisors, I, canines, C, premolars, P, and molars, M. In most primates, the pattern is 2 incisors, 1 canine, 2 premolars, 3 molars. In New World monkeys, interestingly, though, it's 2 incisors, same. 1 canine, same. 3 premolars and 3 molars. Strepsirrhines, it kind of varies. So this is a pattern that probably got set kind of late in the game in primate evolution. That's one thing that tells us. To sort of help you remember it, this dental arcade pattern is one where we start at the front half of the jaw and we count the incisors, 1, 2, the canine, 1, the premolars, 2, and 1, 2, 3 molars. Now this is a human jaw, or mandible, and as we'll find out later, actually, there are several adaptations in the human jaw that distinguish it from all other primate jaws, one of which is the shape of this arch. Instead of having molars that are sort of parallel-sided, ours flare out a little bit. Okay, other common features. The last things we want to point out is that primates have what's called a petrosal bulla. That is a bony covering for the inner ear, just under, in our skulls, it's just underneath here, under the inner ear. You can see in the slide here, it's this slight bump right behind the opening for the ear. In addition, we have, to varying degrees, either post-orbital bars or, for most haplorhines, fully enclosed eye orbits. That is, the bone behind the eye is completely enclosed in a cup, like that. So, whereas for the lemur, there's just this bar that keeps, that gives structure around the eye, but there's no sort of protection behind the eye. And in the raccoon, there's nothing. The eye just kind of sits there. For us, we've got this fully enclosed protective covering. Indicates a couple of things. Importance of visual information in terms of how it perceives the world. Also, how that visual information is becoming more important than olfactory information. So, in fact, actually, although other primates have better senses of smell than us, all primates have worse senses of smell than, say, your dog or your cat. Their primary world is visual, not olfactory. So those are the last things that really define a primate. When you bring these things together, what you see is that they form a sort of basic body plan from which every species varies a little bit. Due to the evolutionary forces at work in its evolutionary history. This is fascinating stuff because, as we'll find out in the next chapter, there have been several really interesting events in that history. So I look forward to telling you more about that. And but for now, take care of yourselves. Hope you have a great week, and I'll see you soon. Bye.